So the next topic is the logarithmic decrement. So this represents the rate at which the amplitude of a free damped vibration decreases. So it's a rate at which amplitude of sorry amplitude of free vibration reduces or decreases. So how do we measure it? We measure the amplitude at time t1 and time t2, and then we take the ratio between them or find out how quickly this is reducing, and we take the logarithmic ratio of that one, two successive amplitudes. So we know that, let's say if a system is under vibration, so there will be vibration like this one going on, but that's just the one aspect of this vibration. All of these waves are represented by a circular diagram through a vector that moves in a circular path called the phasor diagram. This arrow is called phasor. So let's say this was at time t equal to 0. Now the arrow has moved at this point, move at certain degree of angles. Now the amplitude is this one. Now arrow has moved to at time t equals to 3. Let's set 0, t equals to 1, t equals to 2. Now the arrow has reached here at time equals now arrow has reached at this point at time equals to 3. So now it's this one, so on and so forth. So this is how this wave diagrams are formed through a phasor. So this phasor tells us the amplitude of the vibration at different times. Plus, this diagram is not only in 2D, rather it's a three-dimensional diagram. So this is how the actual vibration takes place. So actually that phasor is moving in a circular path like this, one. So this what makes the phasor diagram, and this is how you make the phasor diagram like this one, and this is the timeline. So with the time it keeps on moving forward. So what happens in the logarithmic decrement, if you observe this from this side, what you will see that, let's say the vibration starts from here. Let's say vibration starts from this position and it moves, this phase is moving in a circle, and then it is reducing amplitude with the time, and now that amplitude is even more less, and slowly and gradually it moves towards the 0. So if you see from the other side, and while if you see from the side, it will look like starting from here, this one. So let's say this was your amplitude at time equal to 0. So the amplitude position at this point was x naught, x dot of 0, and you can find out the amplitude at different time. So this is how you can find out the successive amplitudes of any vibrating system. And we know, and we have just seen, that the solution of this vibrating freedom 1 degree of freedom free vibration system is x1, let's say that will be equal to x naught e omega minus of damping ratio omega and t1 cos of omega d t1 minus phi naught. So we have just write 1 minus damping ratio square omega n as omega d. So that's, let's say x1, we have x2, it will become x naught ex1 minus damping ratio omega n t2 into cosine of omega d t2 minus of phi naught. So you can take the ratio of both of these, and here we can say that t2 is equals to T1 plus tau d, that is where this is the period of the damp vibration. It's a time period of damp vibration, which is equals to 2 pi over omega d. Although we need 2 pi over omega, but this is the damp vibration time period, that's 2 pi over omega d. So we can rewrite this expression. So x1 over x2, it will be equals to e exponent minus omega damping ratio omega n of t1 divided by e exponent minus of damping ratio omega n, that's t2, so we can write it as t1 plus tau d, and we can simplify it as e exponent damping ratio omega n, the period of damp vibration. So that's the value of, so the of ratio between the two successive time position at the time different times. So the logarithmic decrement is a natural log of this ratio, that is ln of x1 over x2. It will become equals to, ln will cancel out the nth log, and it will become equals to damping ratio omega n into the damp period of the into the time period of damp vibration. If you want, you can even simplify it further and just open up the value of tau d and just simplify it further, but I think this is sufficient. So you can plot the graphs between the damping ratio and the logarithmic decrement. Sorry, this is represented as, so you can plot the graphs between the logarithmic decrement and the damping ratio. So this tells you, again, this is again the dimensionless quantity, so this will tell you about how the system behavior will change with a changing damping value. Again, why we are using dimensionless number, it eases how we study the system behavior without dealing with the unit systems and balancing the unit system across both sides of equals. So we can do this without getting into this trouble of balancing unit systems. So that's why we prefer dimensionless numbers when dealing with complex system like mechanical vibrations. So this was a logarithmic decrement. Now the last part of this lecture was the complete solution method. Now what will happen if we have a forced vibration? So we'll see this in the next part. Now, before going towards the force vibration, the one of the last topic that we want to discuss is the Coulomb's damping. As I said in the beginning, there are two different types of damping that happens in the field vibration. That's a viscous damping. Another one is a Coulomb damping. That is kind of a friction, the damping because of the friction effects between the two materials. So if we try to draw the general schematic diagram of such system, let's suppose, let's write it, free vibration with Coulomb's damping. Let's suppose you have a mass that is tied to a spring, and that mass is vibrating over a surface, and that surface and the mass has a friction between them. So if you draw the free body diagram of the system, so you have mass and we have applied force in this direction, so system is having some velocity in this direction, so the spring is pulling it backwards, that is kx, and also the frictional effect with the surface is also applying a force in the negative direction, that is mu n, and that's the weight of the body acting vertically downward, and that's a normal force acting vertically upwards balancing the mass. So now what we can do, we can write, we know that the friction force in this case is F equals to mu n, and because normal force is equal to the weight, and that is equals to mass into the acceleration due to gravity. So from here we can derive the equation of motion, that is equals to mx double dot, and that's equals to plus kx plus mu n, or you can equal to 0, and because that's a second order homogeneous equation, and you can again use the same x equals to a e exponent lambda t and take the double derivative and substitute here, so you will reach to a solution, general solution expression of a1 cos of omega n t plus a2 sine of omega n of t minus mu n over k. That will be the general expression uh, for the solution of this such system. So now you can have the different cases for this one as well, but this is the base equation. There's nothing new in the solution methodology. Only thing is now we have a friction damping effect because of the friction. So it doesn't depends on the velocity of the structure, rather it depends upon the normal force and the friction coefficient of the system. So that's all for the free vibration. Now we'll moving towards the forced vibration. Now our next topic is the 1 degree of freedom forced vibration. So let's start how we can solve the forced vibration system, and then that will be the last topic of this general solution method, and then we will move toward the Laplace transformation, and from now on we'll be focusing on the Laplace transformation only to solve the system uh, and to get the steady state and transient response of various systems. So that's 1 degree of freedom forced vibration. So we know that if we have a mass spring damper system and that is being excited at a harmonic force, and let that harmonic force is equal to f naught sine of omega t, and we have a k as a damping constant, c as a k as a stiffness constant, c as a damping constant. So we will have the general equation of motion for our system equals to mx double dot plus cx dot plus kx equals to not equals to 0, rather we have a force f of t, it's better to write it as f of t, and then we can write it as mx double dot plus cx dot plus kx equals to f naught sine omega t, where f naught is an amplitude of vibration and omega is a frequency, and so on and so forth. So that's a linear non-Homogeneous second order equation. So now in the previous case we have this whole system equal to 0 because that was a free vibration, but in this case we have a force that is a harmonic force. So the total solution for the, or the total response to this harmonic excitation can be written as x of t equals to homogeneous solution x h of t plus particular solution, and that's called, and that's the particular solution. So homogeneous solution corresponds to the free vibration part, and then this particular solution is the forced vibration part for that one. So we will solve both of them separately and then combine them together. So we know homogeneous, for the homogeneous solution For this equation we will have to use the same method that we have used before. So if you write homogeneous solution, we can write as rewrite the equation as mx double dot plus cx dot plus kx equals to 0, and then we can have equation of the roots of the equation minus c plus minus under root c over 2m square minus k over m c over 2m and we know that omega n is equals to under root k over m, and this damping ratio is c over c naught, c over cc, where cc is 2m omega n, so it can be also written as c divided by 2m omega n. And we can use the same cases that we have seen before, and we can find the solution of these cases, and at the end we can write as x of t a1 cos of omega t plus a2 sine of omega lambda t, lambda 1 of t and sine of lambda 2 of t. That will be our solution for the homogeneous part. Now the second would be the particular solution. And I will discuss what these two represents physically. So this particular solution, because our excitation is harmonic in nature, so the solution will be of the similar harmonic in nature with the same frequency. So we can write the solution as the general solution for our particular part as x sine omega t minus phi, and we can use we can drive this x dot of p, and it will become so using this general solution we can have a derivation for this one. X particular solution of t equals to a sine of omega t plus b cosine of omega t. That's a simple way to write it up, just to avoid the phase one. And then we can find xp of t and x double dot p of t. So it will become a cosine of omega t minus b omega sine of omega t. There's also omega here, and double dot will be equals to minus a omega square sine of omega t, and that will be minus b omega square cosine of omega t. And we can substitute this in our general solution into our equation of motion, that was equals to mx double dot plus uh, kx plus cx dot equals to f naught of sine omega t. So here x dot is basically xp, and xp. We can substitute this value xp in here and xp double dot here and xp single derivative here. So what you will have, you can separate sines and cosines separately. It will become minus m omega square a minus c omega b plus ka into sine omega t, and then we have another one as minus m omega square plus c omega a plus kb, that's cosine omega t, and this whole equals to f naught of sine omega t. And from here you can we can match the sine omega t with the sine omega t and cosine omega t coefficient with the cosine sine omega t. So here we can say that minus m omega square plus k yeah b plus c omega a, that's equal to 0. And for the sine one, because we have the constant f naught for the sine omega t, so this can be equated with this one. It can be written as minus m omega square plus k a minus c omega b equals to f naught. So we can solve for a and b because that's a simultaneous equation where f naught is a constant value. So that's a constant value, so you don't have to worry about this one. And you have two unknowns, you have two equations, so you can solve this for a and b, and you will have uh, the value for a equals to f naught k minus m omega square k minus m omega square whole square plus c omega square, and then we have b equals to f naught of omega divided by k minus m omega square square plus c omega square. So these are the two values for this is how you can find the constant values, and you can substitute this one into a particular solution. So that was just recalling xp of t, that was equals to a sine omega t plus b cosine omega t, or that was you can write as x of sine omega t minus phi. So this is how you can write down the values. So what are the homogeneous in a particular solution itself? So whenever you excite a system, let's say your system was initially at rest, so when you start applying the force, it will start vibrating. Let's say you're vibrating, and then after some time it will turns it will become a steady state. So in the beginning the amplitude was slightly increasing, progressively increasing until it reaches a constant value, and then it maintained that amplitude until you are applying force f naught sine omega t. But this region where the system was still stabilizing, that's called the transient part. And this region where the system has stabilized, that's called the steady state. So the homogeneous solution gives information about the transient solution, while the particular solution tells us about the steady state solution. It tells us about the steady state one. So when you combine both of them together, it tells the whole solution or whole response of a system in the transient domain as well as in the steady state domain. So until the system has not stabilized, that that solution or response of a system up till that time, that would be considered as a transient response. And once the system is in a steady state position, it is vibrating with a constant amplitude or it has come to rest, we call it to be a steady state response of a system. This is what we are interested in longer term. It depends upon what you want to study. In some cases you are concerned about the transient response of a system. Let's say you have a shock absorber, so how the system will respond as soon as the force is applied onto the shock absorber of a car. But for, let's say, bridge, you are more interested in the steady state response of a system, how this bridge will respond for a longer period of time. So it depends upon what kind of response you want to study, or you may combine both of them together. That if a bridge is forced by the gust of wind, so how will it respond in the beginning, and how it will respond for time t equals to 2 hours or 10 hours. It depends upon what you want to study. So this is a way to calculate the response of a system through force vibration. So there are again some ratios for this one. Uh, there's a ratio which is the ratio between the omega, the frequency of the force vibration, and the omega and the natural frequency of a system. And we have the steady state amplitude. We can write it as f naught of under root k minus m omega square plus c omega square. And you can find the phase angle, because what the phase angle means, once the system is vibrating, or let's say this mass was vibrating back and forth, and you are applying the force that is also vibrating back and forth. So maybe in the beginning, when the force was moving in this direction, the mass was also moving in this direction with the same amplitude, with the same velocity. But after some time, because of damping, now, or because you have reached near to the resonance state, now it happens like when you are applying the force, the system is moving backward, and then when you are removing the force, system is moving in this direction. You can practically observe this one if you apply force on any elastic structure. So you will keep on applying the force. Let's say there's a bridge, and you keep on applying the force onto that bridge, the harmonic force, let's say with 10 hertz frequency. So at in the beginning, maybe the bridge will move down when the force is acting downwards, and when the force is removed, bridge will move up. But after some time, there will be some lag between the applied force and the movement of the bridge. Maybe you're applying the force downwards, and at that particular time, the bridge was moving upwards from its extreme position. So your force collides with the upcoming bridge. And once the force is removed, bridge is at that point is actually started to moving away from the equilibrium position towards extreme position. So there's a lag between the applied force and the response of a system. That lag is called the phase angle. So you can find the phase angle by tangent phi c omega divided by k minus m omega square. So that's all for the vibration system using the general solution method. We have seen the 1 degree of freedom, we have seen the 2 degree of freedom. I will share some derivation, not the solution, but a derivation of a second order or the second degree of freedom system, where we have 2 degree of freedom using the general solution method, how you can drive the mathematical model. But we are not going into the solution for that system at the moment. The next thing we are going to cover is the Laplace transformation. What's a Laplace transformation? If we learn to use a Laplace transformation, we don't need to deal with all of this complex mathematics. It will directly turn this differential equation into an algebraic equation, and then you can use a simple algebraic methods to solve the system and find the steady state and transient response. And then you can use the inverse Laplace to bring it back into the time domain. So Laplace deals with the frequency domain only, so you have to convert that into the time domain after you have reached a solution. So there's a particular technique for you how to we can do it. We will see this in the next lecture.